The biggest explosions humans have ever seen and recorded, with a brightness that can exceed that of 10 billion suns, outshining their galaxy with average temperatures of 600 times the sun's core. That is 1 billion Kelvin. So, how does something like this happen? Well, in a simple term, it's the death of a star. To put it in a complex way, there is a balance of gravity pushing in on the star and heat pushing outwards because of the pressure in the core. The flame is due to mostly helium and hydrogen reacting, but this will eventually have to come to an end, and the pressure has to drop due to not being able to hold all that pressure in. However, it drops so rapidly that by the time the pressure is lost, an enormous heat-fueled pressure shockwave is released. In 1938, Walter Baade became the first astronomer to identify a nebula as a supernova remnant, and it was when he suggested that the Crab Nebula was actually the remains of a star, and this star was called SN 1054. Just don't forget that the person who discovered nova stars is Nova Hercules. One of the brightest novas of the 20th century was discovered in 1934, but that's another story. Now, these explosions, bearing in mind how far away they are, can sometimes be seen by the naked eye, and the most recent supernova that was visible to the eye was called Supernova 197A in the year 1987. It was approximately 168,000 light-years away, and before that the last supernova visible to the eye was in 1604, which was also approximately 168,000 light-years from Earth. Now, this may seem like a long 383-year gap, but in space, that is a very, very, very short amount of time. Because of all the pressure going to the core, it holds up to around 1/3 of its mass in that single area. This is also known as a white dwarf. And fun fact, 1 teaspoon of a white dwarf would weigh around 15 tons. This is because something like the mass of the Sun would turn around the size of Earth. This has an average common occurrence of once every 50 years in galaxies similar to that of the Milky Way, meaning every second or so there are these phenomenal energy releases everywhere. There is a cluster of these called the local bubble that surround the solar system, and its visuals are incredible. To get into further detail about supernova, they can go one of two ways. Type 1 being that the star accumulates matter from a nearby neighbor until a runaway nuclear reaction just simply ignites. And Type 2, the star runs out of nuclear fuel and simply collapses under its own gravity. Now, of course, the more interesting one to look at is Type 2. It has to be several times more massive than the Sun to be able to cause such a heavy, bright, and powerful explosion. And just like the Sun, it will eventually run out of hydrogen and then helium fuel at its core. But it will have enough pressure and mass to fuse carbon in the core. Now, you can imagine that with all these heavy elements that are piling up and being pressurized into the core, it sort of looks like an onion if you were to slice it in half. The lighter the element, the further from the inside it will be. Now, as this happens, the core heats up and becomes denser, and eventually the implosion bounces back off of the core, expelling this stellar material off into space. And that, in full detail, is what forms the supernova. Now, I've only been showing you a more common-sized supernova. These stars have so much pressure that if they were to explode the way normal stars do, the implosion probably would cause a black hole if the right size. This may not be true, this is just a personal assumption, because the mass of these entities and the energy required to put all of that mass into such a small space is almost comparable to a black hole. If you'd like further information on how black holes work, you can check out my first video. If you're more interested in exoplanets, take a look at my second. Thank you for watching.